Hello. In this video, I will discuss Lab 4, Circuits and Capacitors, in which we examine the different properties of DC and RC circuits using a circuit modeling software. The objective of this lab was to examine how resistors operate in series and in parallel, and to also examine the properties of an RC circuit using circuit simulation software. Important equations used in this lab include Ohm's law, delta V equals IR, along with delta V equals Q over C for capacitors, and a linearized equation for the voltage of a discharging capacitor given by the natural log of delta V over delta V naught equals negative T over RC. To start this lab, I first modeled a DC circuit with two 1.5 volt batteries, two resistors placed in series, and an ammeter placed before and after the resistors. The actual model for this circuit can be seen below, which I generated using a circuit simulator. The current at I1 and I2 were measured to be 0.02 amps. This makes sense as the node rule states that the current in equals the current out. The change in voltage across the circuit measured using a voltmeter can be seen on the right. The battery has a positive slope as the battery increases the voltage by 3 volts. The wires and ammeters all have slopes of 0 because there is no change in voltage in these portions of the circuit, meaning that the delta V is 0. The first resistor has a negative slope due to a change in voltage of negative 0.96 volts, and the second resistor has an even steeper slope due to a change in voltage of negative 2.04 volts. Using Ohm's law and the data from the previous slide, I calculated the resistance for the weaker resistor to be 48 ohms, the resistance for the stronger resistor to be 102 ohms, and the resistance for the wire and the ammeter to be 0 ohms each. One circuit variation we made was when an ammeter was placed in parallel with the 100 ohm resistor. When doing this, we measured the current at both ammeters to be 0.06 amps. This makes sense because the ammeter in parallel provides the current with a path to travel which has no resistance, meaning that the current will avoid the 100 ohm resistor altogether, thus increasing the overall current. Another circuit variation we modeled was when an ammeter was replaced with a voltmeter. In this model, the voltage was measured to be negative 3 volts and the current was measured to be 0 amps. This makes sense because voltmeters must have very high resistances for them to work correctly. We also modeled charging RC circuits using one 9-volt battery, one light bulb, and one 0.2 farad capacitor. When using a light bulb with a resistance of 10 ohms, it took 5.5 seconds to fully charge. But when using a light bulb with a resistance of 20 ohms, it took 10.2 seconds to fully charge. This makes sense as the capacitor took longer to charge when the circuit contained a stronger resistor. We also modeled a discharging RC circuit using one 9-volt battery, one light bulb, and one 0.2 farad capacitor. Using a light bulb with a resistance of 10 ohms, it took 5.1 seconds to fully discharge, and using a light bulb with a resistance of 20 ohms, it took 13.2 seconds to fully discharge. This makes sense, as a capacitor with a stronger resistor should take longer to discharge. The voltage of a discharging circuit can be modeled by delta V equals delta V naught times e to the negative t over RC. When linearized, this relationship can be graphed to easily calculate the RC value of the circuit. To graph this relationship, we measured the voltage of a discharging circuit with a 0.2 farad capacitor and a 30 ohm light bulb over 20 seconds to determine the circuit's RC value. We used the line of best fit for this linearized data to find the slope. From this slope, the RC value for the circuit was then calculated to be 6.01323 seconds. This is quite close to the expected value of 6 seconds. On this slide, you can see the voltage data we collected over the course of the 20 seconds, along with the linearized graph and the line of best fit we found. To summarize this lab, if an actual ammeter was used instead of an ideal simulated ammeter, then the current across the actual circuit would be lower than the current in the ideal circuit. This is because actual ammeters have resistance, and therefore a voltage drop would occur across each ammeter. Also, If a capacitor were charged in an ideal circuit without a resistor, then the charge would occur instantaneously. This wouldn't occur in real life, however, because batteries have some small resistance which would prevent them from immediately charging and achieving this maximum voltage.